Hi again, guys. So on the menu now is chapter 14. We're gonna basically pick up where we left off from chapter 13, cardiac function. Today it's about the vascular system um, pertaining to specifically blood vessels. So when you think about it, CVS, let me kickstart so this word here, the three letters CVS, this has nothing to do with the pharmacy chain. This stands for cardiovascular system. So cardio means the heart. Vascular means your vascular beds, your blood vessels. So chapter 13, we were basically looking at how the heart, the two components of the heart, the electrical component and the mechanical component were being controlled, being affected. For chapter 14, we complete the system. Now we're going to take a look at the blood vessels, the vascular beds. In other words, how is blood flowing through these vessels? So to put it simply, we're going to look at factors that are basically can affect how blood flows. So at the end of the chapter, I'm hoping that you understand what is the driving force, what is the engine, what is the force pushing blood through the blood vessels, through the vascular system. Right? I'm not going to jump the gun telling you right off the bat the answers to that. So our job today is basically going through it step by step and trying to understand and appreciate the second half of this beautiful story about this amazing organ system, the cardiovascular system. If I didn't specialize in neurology, I would have gone to this particular becoming a cardiologist. That would be also awesome. So it's amazing organ system. So I hope you will appreciate this and then see how you can basically connect the dot, bringing back chapter 13 and put it together with chapter 14 as a whole, a complete picture. So with that said, the learning objective is try to understand three pillars here. So first is blood flow depends on what are the factors affecting blood flow. So there are factors that are basically part of the cardiovascular system, for example, part of the blood vessels. So we call that intrinsic control mechanism. Intrinsic means it's basically part of the something. There are also other factors that are not part of the cardiovascular system. They come from, for example, the nervous system. They come from the endocrine system. So other organ system coming in to affect this blood flow. We call these mechanisms extrinsic control mechanisms. So that's the second pillar on the learning objective, right? So the first mechanism is the intrinsic control. These are ingrained into the cardiovascular system. The cardiovascular system have these in place, right? The heart, we saw it in chapter 13. Today, we're going to see that in the blood vessels. They have this capability of self-controlling their activities. The other factors outside the cardiovascular system, we call it extrinsic factors. So these factors come from the nervous system, and also they come from the endocrine system. So two additional organ systems outside of the cardiovascular system coming in to have a say, to have a control, to have a regulation, how fast, how slow your blood will flow, okay? That's why underneath here you see neurotransmitter. So that's the chemical messengers released by the nervous system affecting vascularization or hormones, chemical messengers coming from the endocrine system performing the same objective, meaning affecting blood flow. And the last pillar of the lecture is about how to regulate this concept that we call mean arterial pressure, MAP, affectionately called MAP, but this has nothing to do with the regular MAP, right? So this MAP is extremely, extremely important. Again, I'm not going to say you right off the bat what this MAP does, but toward the end of the lecture, this is, if you can appreciate it, it would be great. So this MAP is highly, highly regulated, okay, by the nervous system and by the endocrine system. So that's the three main objective for the learning objective for the lecture on chapter 14. So let me erase this before I move on. Otherwise, I'm going to carry over to the next slide. And then moving on to the first slide. So we're going to start off with blood flow being controlled by the blood vessels themselves. So the first, there are actually four mechanisms, four intrinsic mechanisms. The first one is called active hyperemia. The word hyperemia simply means anything pertaining to an increase in perfusion, an increase in blood perfusion through an organ. Okay, so in other words, an increase in blood flow. Now, what is amazing is let's pay attention first to panel A, this panel here. So under normal homeostatic conditions at rest, you will have tissues that are producing, that are consuming the same amount of oxygen that's being delivered by the blood vessels. And the same amount of carbon dioxide being produced by these cells, it will be picked up, disposed by the blood vessels. The cells would consume the same amount of nutrients that's being delivered by the blood vessel. Same thing. The disposal of the waste, the cellular waste coming from the cell, picked up by the blood vessel, also are equal. So we are talking about a steady state at equilibrium. Anything that goes out the blood vessel equals the amount that comes into the blood vessel. Anything that goes into the systemic body cells equals the amount that comes out of these body cells. Under these conditions, blood flow stays the same. The blood vessels stays the same in terms of diameter. Now imagine a case, okay? Imagine now that suddenly your metabolic activity increased. So we move on to panel B. So your question to me should be, okay, dude, why did the metabolic activity of the cells increase? Think about it. If you start to exercise, right? So when you exercise, your cells consumes more oxygen, consumes more nutrients, produces more carbon dioxide, produces more cellular waste. So suddenly now the cells, the systemic body cells, generate more cellular waste, generate more carbon dioxide than the blood vessels can pick them up, require more oxygen consumption, require more oxygen because of due to increased consumption of oxygen, require more nutrients than the blood vessels can deliver oxygen and nutrients. Right? So we have a problem here. So the blood vessels can detect that amazingly because of the release of these chemicals. Let's say, for example, carbon dioxide accumulation, oxygen depletion will lead to panel C here. So what's going to happen now is the blood vessels will respond, right? the blood vessels, the smooth muscle in lining in the wall of the blood vessel will relax. In other words, the diameter of the blood vessels has been increased. So in other words, the blood vessels becomes bigger. So there are more room for blood to come in. So now we have an increased blood flow, right? So if you have an increased blood flow, over here, panel D, now more oxygen can be brought in, more nutrients can be brought in and delivered to needy body cells, and more carbon dioxide and more cellular waste can be picked up by the blood vessels, right? So bringing back homeostasis. So now again, the amount of oxygen consumption equals the amount of oxygen being delivered by the blood vessel. The amount of nutrients consumed by systemic cells is also equal to the amount of nutrients being delivered by the vascular bed. The amount of carbon dioxide produced by systemic cells and the amount of cellular waste produced by the systemic cells will be equal to the same amount of carbon dioxide and waste picked up by the blood vessels. Now we have homeostasis. Everybody's happy, right? So this, we call it active hyperemia. In other words, blood flow will increase to meet the metabolic demands of cells under increased cellular activity. For example, during a vigorous exercise, right? So that's for hyperemia, the first factor, intrinsic control mechanism controlling blood flow locally within the vascular bed. No external player, no external factor was involved. Moving on to mechanism number 2. Now this mechanism is called reactive hyperemia instead of active. In this case here, the cause is not about metabolic activity. The cause is not about increase in terms of metabolic activity of some systemic cells. The root cause here is due to blood flow suddenly drops, right? So you're not exercising, you're not doing anything, you are at rest, and suddenly blood flow, blood perfusion through systemic tissues decreases, drops. So your question to me is, okay, why, right? Critical thinking here. So don't learn anything blindly. So you should ask, okay, dude, why? Why do we have a sudden blood drop, right? Blood flow, blood perfusion dropping in systemic circulation. The easiest answer to that question is you have a blood clot. Somewhere, somehow, whatever reason, one of the blood vessels is being occluded, being blocked. So blood perfusion through that blood vessel is significantly compromised. Okay? So if that's the case, so what's going to happen is, so when your blood flow is compromised, when blood perfusion decreases through a tissue, we have the same concept apply from now on out. So the root cause might be different. The previous one is increased metabolic activity. This one is due to blood perfusion, being dropped. The response is the same. So the cells, now even though they're producing at base or resting rate, oxygen is being consumed faster than the blood can deliver because blood perfusion has been compromised. So there's less oxygen coming in. Same thing with nutrients. If there's less blood coming in, less nutrients will be delivered to cells. So the cell will be compromised in terms of oxygen, compromised in terms of nutrients delivery, and then they produce oxygen, carbon dioxide, CO2, and cellular waste that will also accumulate because due to the decreased blood flow. So there's less carbon dioxide being disposed, taken away, less blood to pick up cellular waste. So now the blood vessels also need to react. So from that point on, the mechanism is the same between reactive hyperemia and active hyperemia. The blood vessels will dilate, allowing more blood to come in, delivering more oxygen, delivering more nutrients, picking up more CO2, picking up more cellular waste away from systemic tissues, restoring homeostasis. So that's why down here, the mechanism between the two are identical, okay? This one is active hyperemia. This one is reactive hyperemia. Reactive hyperemia, the root cause is decrease in blood perfusion. Active hyperemia, the root cause was increased metabolic rate due to an increase in cellular activity. So that completes the first two intrinsic mechanism to increase blood flow, to prevent accumulation of CO2 and cellular waste. The third mechanism, the third intrinsic mechanism that blood vessels have, this is very similar to the heart. Remember, the wall of the blood vessels, we have smooth muscle. This you must have learned it from anatomy. And the wall, the heart, I do hope for you that you know this, is basically cardiac muscle, right? Both of these types of muscles, cardiac muscle and smooth muscle, they have a beautiful, beautiful ability. When you stretch them out, they respond by constricting, right? So when you stretch the wall of the blood vessels out, the smooth muscle will contract. In this case, we call it constriction, vasoconstriction, meaning your blood vessels, the diameter of your blood vessels become smaller, okay? So contraction in the vascular bed means we call it vasoconstriction. So whenever the smooth muscle wall in the blood vessel would be distended, would be stretched out, the smooth muscle will respond by constricting, decreasing the diameter of that particular blood vessel. Okay, so this is called myogenic response. SM up here is for smooth muscle. Okay, so that's the third mechanism. I hope I didn't forget anything. Okay, let's imagine something here. I think it's worth an example. So I'm drawing out, sorry for my hand drawing here. So I'm drawing two different blood vessels. Okay. Now, blood flows here, through here. Blood flows through here. Now this one and this one, those two blood vessels have different diameter. The top blood vessel, the diameter is smaller. And the bottom blood vessel, the diameter obviously is larger, right? So this is physics. This is laminar flow. If there's a liquid flowing in the tube, and if the liquid flows in a small tube, it will meet a higher resistance to its flow than if the same liquid flows in a larger tube. So in a larger tube, that liquid would basically be met with less resistance to its flow, right? So when you that's why it explains here, that's the reason here, increase perfusion pressure. So when the pressure pushing blood forward is increased, right? So stretch of arterial smooth muscle here, your blood vessel will be stretched out. They will respond by constricting, right? So whenever the pressure that pushes blood through a blood vessel increase, it tends to expand the wall of a blood vessel. And when that happens, that wall is not passive. That wall will respond. It's like somebody slaps you, you don't let them slap you, right? You hit back. It's the same thing here. So if you basically try to expand the blood vessel will respond by constricting back. This is exactly what happens. So when you constrict back, you increase the resistance and you decrease the flow, right? So if you basically, so this is under high pressure. So if this is basically delta P, pressure gradient, okay, is increased, the blood vessel will constrict and it will lead to this, going back to its initial state here, okay? So this is controlled by a negative feedback. This is a beautiful example of a negative feedback. Intrinsic control mechanism. Doesn't need intervention of the nervous system, doesn't require the regulating mechanism involving the endocrine system. It does it on its own, instantaneously, okay? So that's your third intrinsic mechanism. Beautiful capability from both smooth muscle and, as we saw also during chapter 13 handout, the myocardium, the cardiomyocyte in the wall of the heart. Both cardiac muscle and smooth muscle respond when you stretch them out. So moving on to the fourth and last intrinsic mechanism. This is the release of chemical messengers. This one is very straightforward. You're gonna learn this as is. There's so much detail here. So it saved me some time to go on to explain other important concepts. This is redundant here. This information, you have it already on the table here. So learn this table as is and remember local, vasoactive, meaning these are chemical messengers that will cause a reaction from the vascular bed. So vaso means blood vessels, right? So either they're gonna dilate the blood vessel, the vascular bed, or they can constrict the vascular bed. So vasodilation here means dilating the blood vessel. Vasoconstriction means they're constricting the blood vessel. There's one thing that I would like to add. I thought I knew I forgot something. This book, oh yeah, never mind. I'm gonna confuse you. Ironically, the most powerful vasoconstrictor naturally produced by the body is not on this list. That's food for thought, right? Why is that chemical not on this list? It is the most powerful, one of the, if not the most powerful among all of them on this list here. Those who basically vasoconstrict a blood vessel, the most powerful one. Why is it not on here? Okay. It's called angiotensin 2. The reason for that is because angiotensin 2 is a chemical released by another organ system. So it wouldn't fit the bill here because we're talking about intrinsic mechanism. Okay, so that's basically forcing you to connect the dot, right? That would have been a beautiful question, right? Maybe at the beginning of the semester, now you are all expert now. You know my way of thinking. So, you know, I think 95 of all of you would nail the question. But that's one of an example of a critical thinking question, showing you how to connect the dot between different lectures. Okay, moving on to now mechanisms that are affecting blood flow, but they come from other organ system. So before we talk about it, let's basically briefly review about, you know, fluid flow in a tube. This is basically, again, one of the basic mechanisms of mechanics and physics. So think about a tube and then water flowing through that tube. So I briefly explained earlier. So the smaller the hose, the smaller the diameter of a tube, the higher the resistance to a liquid flowing through that tube. So if you increase the diameter of that tube, the resistance to flow would drop significantly. Okay, so if you look at the tube A and tube B, so the diameter in the case of the tube A is, you know, obviously larger here than in B. Visibly, you know, obviously smaller diameter than A. Now pay attention here, okay? There's no flow. If you don't give an incentive, there's no flow. So if you start to see liquid flowing, it means somewhere, somehow, there must be a force. There must be an engine. There must be a driving force pushing that liquid through a tube, right? So the engine driving this flow is a pressure gradient. In other words, delta P here. So this delta P is the engine, the motor, the force that drives a liquid moving from point A to point B. Now, when we say gradient, we means it will move from a higher pressure point to a lower pressure point. Okay, so let's call this compartment 1 and compartment 2. Compartment 1 has more liquid than compartment 2. So because of that, compartment 1 has a higher pressure than compartment 2. So the delta P, this value is the most important one. You don't care about how much this pressure is. You don't care about how much this pressure is. What you care about is what's the difference between the two pressure. Because that difference is what drives the fluid from compartment 1 to compartment 2. So that delta P 40, let me demonstrate this. So let's say this compartment 1, you have 100 millimercury versus this one, you have 60 millimercury. The pressure gradient is at 40. Now, if you change that, okay, instead of 100, you increase it to 200. So the pressure here in compartment 1 is 200, and this one is 160. You still have the same pressure gradient of 40. You see what I meant by that? So you don't care about the absolute pressure in compartment 1. You don't care about the absolute pressure in compartment 2. What are you're interested in is what's the difference between the two pressure? Because that difference will be the force driving a liquid through a tube. And that relationship is beautifully described here. in a mathematical relationship, okay? F stands for flow. So you have the flow of a liquid, and that flow depends on two factors, okay? The first factor is the driving force. So the reason why you have a flow is because of that driving force, delta P. Now that delta P, unfortunately for us, is not free flowing. It will have a resistance to its flow. And that's expressed by R, resistance to flow. So the higher the delta P, the higher the flow. So the relationship between delta P and flow is proportional. The relationship between the resistance in flow is I forgot how to say this. Indirectly proportional. So the higher the resistance, the lower the flow. Okay? So that's the relationship. So flow is dependent on two factors. Delta P driving the fluid forward, resistance, that's the force that opposes flow. Okay? So the stronger the gradient of pressure, the higher the flow. The lower the resistance, the higher the flow. And vice versa. The lower the delta P, the flow will decrease. The higher the resistance, the flow will also decrease. Erase this. Okay. Let's play a little bit about with that equation. Flow here in the in human physiology comes back as cardiac output. Okay, this is the amount of blood being pumped out by the heart per unit time. We learned in chapter 13, cardiac output. We also learned that CO, cardiac output, depends on two factors. HR, heart rate, times stroke volume. We also learned from chapter 13. Now this delta P is the map here. Okay, so that's the driving force. And this resistance is expressed over here. Total peripheral resistance, TPR. Okay. Now, if you pay attention, we can rearrange this equation over here. So MAP equals cardiac output times total peripheral resistance. Since CO equals HR times SV, you convert that over here, down here. You see MAP equals SV times SR. This here is your CO. Okay, so that CO is right here. So instead of saying CO, you plug in CO HR times SV. So MAP is the driving force pushing blood through our vascular bed. There you go, right? MAP. Mean arterial pressure. Okay? Mean like the average arterial pressure. Now let me erase this and then put a story to these equations, because you never want to learn these equations as face value, because it's meaningless. You need to put a story, like you need to put a name to a face, right? So it gives you a mental picture so you can appreciate the relationship. So allow me to go back here to write cardiac output equal HR multiplied by stroke volume. Now we learned from chapter 13, the heart, and this is a beautiful, what I'm about to say here, so pay attention, okay? Wake up, okay? Or you can stop the lecture, get a coffee, take a break, smoke, go take a cigarette, and then come back. But I want you to be fresh here. So we talk about this in chapter 13. The heart has two components, right? A mechanical component and an electrical component, okay? So both the electrical component and the mechanical component work together as yin and yang, as man and wife, as a team to pump blood. That's the function, the raison d'etre, you know, the why the heart exists is to do that, is to pump blood, to create a pressure so blood can flow forward, okay? And that pressure generated by the heart, we call that cardiac output, right? So amount of blood pumped out by unit time. Now the beauty in that, the two components is, if you look closely, HR, the heart rate, that's your electrical component of the heart, okay? So two components, right? Electrical component, the conduction system, it is expressed by HR in this equation. And the other one, the mechanical component, it is reflected, expressed, represented by SV, stroke volume, the strength of the contraction. Every time the heart beats, it sends out a defined volume of blood. And that is your mechanical component of the heart. So when we say CO equals HR times SV, you can learn it like that, but you won't appreciate the story behind that. The equation is telling you, okay, the heart depends on has two players here, two components, right? Its function depends on its rhythm and also the strength of its contraction. It takes both. It takes two to tango here. It takes two so the heart can do its job. So that's what I want to emphasize, that I think I didn't make it myself clear enough when I talk about this in chapter 13. But since in the context of this, I think it's refreshing to hear it again. And every time that I have a chance to show you a mathematical equation, I always tell you the story behind this. So this is a trick for you also. If you go on to take a math course, this is try to put that, because every single equation has a story to tell. So if you can, get it right, okay? Don't ever memorize a math equation. This is like you fail to appreciate something beautiful every time you get a chance to see it, right? Well, that's me. It sounds so nerdy. You know, it sounds so nerdy, but that's how, you know, you see things. So every time you see a mathematical equation in biology, grab it. Try to put a story behind it. Okay, going back to reality here. So, can I erase this? So again, going back here. So map now the driving force for blood flow depends on three factors. This is how do I say this? Checking that carbon, stop saying carbon, dude, sorry. Cardiac output equals stroke volume and heart rate to the next level. Now, we are not talking about the heart. We are talking about blood vessels, right? Blood flowing through blood vessels now, because when we talk about the heart, it's blood being pumped out of the heart and they go through the blood vessels. So now the center of attention, you know, the star of the movie is about the blood vessels. So the force driving blood forward depends on three factors. One, two, and the third factor. Factor one and factor two, you know about it. Now we introduce the third factor, TPR, total peripheral resistance. The first two factors comes from the heart. The mechanical component and the electrical component of the heart. The third factor comes from your blood vessels, the vascular beds. Now you see why we talk about cardiovascular system, CVS. Okay? Cardiovascular system, the heart and the blood vessels come as a team for what? Come as a team to drive blood forward, to perfuse every single tissue in the body, bringing oxygen to the tissues, bringing nutrients to the tissues, bringing and disposing cellular waste for the tissue, picked up carbon dioxide for the tissue. Okay? So you need that blood perfusion, you need that blood flow. And that the reason why blood flows in our blood vessels is because of one driving force. And that driving force is MAP. And that driving force depends on the three factors, two of which comes from the heart, and the third one comes from the blood vessel. The blood vessel can constrict, the blood vessels can dilate, affecting blood flow. That's the power of this equation. MAP equals SV multiplied by HR multiplied by TPR. In English terms, the force driving blood through my blood vessels depends on three factors, two of which comes from the heart, the electrical component of the heart, the mechanical component of the heart, and the third factor depends on the blood vessels. How strongly are they constricting? Are they constricted? Are they dilated? Affects blood flow. Okay? So that's the story behind that equation that I want you to appreciate. Okay, next. These are external factors coming in to affect blood vessels. So we have two organ systems that do have a say that they can control our vascular bed. So when you see here norepinephrine, this is coming from the nervous system. And when you see epinephrine, This is a gray zone here. This it's from a sympathetic response. Okay. Sympathetic, this is a sympathetic division of the autonomic nervous system. Autonomic, ANS. Right, so this is a motor division of the nervous system. So it is from the nervous system. However, and this is tricky, okay? Epinephrine is released by an endocrine gland, the adrenal gland. More specifically, the medulla of each adrenal gland releases this epinephrine. And this epinephrine is released into our bloodstream. So in that case, under this context, epinephrine is not acting as a neurotransmitter, even though it was induced, meaning its release was induced by the nervous system. But functionally speaking, when it is being released, it's acting as a hormone. Right? So in this case, epinephrine is, that's why I said it's a little bit of a gray zone. It was induced by the nervous system, yet it functions as a chemical messenger belonging to the endocrine system. Okay? So that's why you see the title there, neurotransmitter versus hormones. This table here, you're gonna learn it as is. I'm gonna emphasize something here because it's not really clear. The norepinephrine is released as a neurotransmitter, NT, right? And that neurotransmitter, that norepinephrine is released by post, and this from anatomy, post ganglionic fibers. Meaning, it is released by axon terminals that belong to the postganglionic neurons, right? And these postganglionic neurons, they belong to the sympathetic division of the autonomic nervous system. So they release this neurotransmitter, this type of neurotransmitter called norepinephrine or noradrenaline, into a neuromuscular junction, not a synapse, because we're talking about the space, that microscopic space between a neuron and a effector organs. In this case, it's a cardiac, for example, cardiac muscle cell, cardiac muscle fiber. It can be a smooth muscle cell, okay? But we are not talking about between neuron and neuron, so we cannot use the word synapse. That's one thing that I want to emphasize. The other thing that I want to emphasize is the different responses for the different adrenergic receptor, alpha and beta 2. So we're going to go back to that later. So put that back in the put that in the back burner. So we're going to focus on alpha 1, and we're going to focus on beta 1 and beta 2. Okay. There are alpha 1, alpha 2, beta 1, beta 2, beta 3. But in the context of what I'm, lecturing, the relevant to my lecture is basically these three: alpha 1, beta 1, and beta 2. And this is in a critical junction here. You need to go back and connect the dots because we've learned them, from, I think, chapter 8 and also chapter 5. So as we go through the lecture, and if I can recall these figures and pages, I will share that with you when we get there. But this is important for you to go back and refresh your memory. These, all three of them, we are talking about G protein coupled receptor. Okay, we're going to talk about that when we get there. But keep that in the back burner. So epinephrine, it can activate both alpha and beta with completely different responses from the cell, and also depending where the type of tissue is. So it gets very interesting if we go stepwise and not jump straight to it. So I'm going to walk you through it, and then you will believe, trust me, you will love it. Okay. So now we're gonna keep on going, but now we're gonna go over focusing on MAP, that driving force that pushes blood through, right? So this equation again comes back. So you have MAP, mean arterial pressure, driving blood flow, driving blood forward in the vascular bed. Okay, this is important here. MAP drives blood through the blood vessels. Not, okay, so what I wanted to say is not through, yes, through the blood vessels, so through the arteries, through the capillaries, and through the veins, and so on and so forth. Because by the time, the beauty about this is by the time it gets back to the heart, by the time blood gets back to the right atrium, the entry of venous blood into the heart, MAP is exactly 0. That's the beauty, right? When it comes out of the aorta, it's around 120 millimercury. But when it comes back to the superior and inferior vena cava, it's exactly 0. So MAP drives blood through the vascular bed. If you can come up with the next question on your own before I say it, you've understand a lot. The similar question, the follow-up question is, then what drives blood through the heart? Right? So when we talk about the heart, we need to be careful here. What type of blood are you talking about? Blood flowing through the chambers? Or are we talking about the coronary circulation, meaning blood flowing through the blood vessels that are feeding cardiac muscle tissue, right? So the question is, what drives blood through the chambers, through the atria and through the ventricles? It's actually the heart itself. The mechanical component of the heart is basically pumping blood. But in the vessel itself is MAP, mean arterial pressure. It's indirectly from the heart, obviously, because of these two factors here, HR and SV, that's the heart, right? So HR, the electrical component of the heart, SV, the mechanical component of the heart. So the heart does generate that pressure gradient, drawing blood through the blood vessel. Okay. So we're going to talk about this, and we're going to pay attention. So any factor that will affect heart rate will affect MAP. Anything that affects stroke volume will also affect MAP. Anything that will affect TPR will also affect MAP. Right? So that engine has three components helping it to drive blood forward. Okay. So the first one, let me erase this. So the first external mechanism coming from the nervous system, we call this neural control of mean arterial pressure. You need to go back a little bit about from your anatomy. There are within our vascular bed, there are locations where we have receptors that are exquisitely, beautifully sensitive to fluctuations in the pressure of our blood. So they're very, very, very sensitive to blood pressure fluctuations. And they are strategically located, right? One such location is exactly located at the arch here of the aorta. We call that the aortic arch from anatomy, right? So you have receptors there, and they're called baroreceptor. So they are basically receptors detecting sensitive to pressure fluctuation, pressure changes, right? Arterial is because they are located in arteries as opposed to capillaries and veins. That's why we call them arterial baroreceptor. So one of which is located in the aortic arch. The other locations are at the bifurcation at the carotid artery. So the common carotid artery, before it splits into external and internal carotid arteries, we have a chamber. We call it a sinus. And we call that those carotid sinuses. In the walls of the carotid sinuses, we have these baroreceptors that are basically sensitive to blood fluctuations. And it is strategically, positioned because at these three locations it's important. Because why at the aortic arch? That's the pressure. It needs to be strong enough to basically drive blood through the rest of the body, through the rest of the systemic circulation. And the systemic circulation has a lot of distance to cover. So again, the longer the tube, the higher the resistance to flow. Therefore, the pressure needs to be higher than that resistance. Otherwise, blood will not flow, right? So in order for the brain to be notified and to adjust the stroke volume from the heart, it needs to know what is the pressure at that moment in that aortic arch, right? And interestingly, if you puncture that aortic arch, the pressure inside that blood vessel is so strong that it will eject the blood 6 feet above your head, right? That's to give you an idea about the pressure inside that blood vessel. If you poke a hole in there, God forbid, there's a jet of blood strong enough to push blood out as a stream of blood coming out, like at the end of a hose, water hose, 6 feet above your head. It goes 6 feet above your head. Okay? So that's how strong the pressure in that blood vessel. The other two location, the carotid sinuses, is because that's the entry into your brain. So those two blood vessels transport blood, perfuse your brain. And in fact, there's only 4 blood vessels perfusing the entire brain. The right and the left, internal carotid. What are the 2 other blood vessels perfusing the brain from anatomy? I'm going to wait like a few seconds for you, see if you can come up with an answer. If you do, here are the answers. The other two is basically the vertebral arteries. They go through the transverse foramina in your cervical vertebrae, right? Those are the landmarks unique to the cervical vertebrae. On the side of each vertebra, you have two additional holes, right? And those two holes are basically where the vertebral arteries are running through these transverse foramina, and they go into the brain to perfuse your brain. So the two internal carotid and the two vertebral arteries perfuse your brain. Okay. Now, how does it work? Now, when your blood, under normal conditions, when the blood vessel, the wall of the blood vessels are not being overpressured, so in other words, they're not being distended, or the blood pressure hasn't dropped, it's normal. So action potential will send to the medulla oblongata, that's the cardiac center in the brainstem controlling this. So it receives a a defined number of action potential per unit time. So this is the baseline frequency, okay? So under normal blood flow, under normal homeostatic conditions, this is how much action potential per unit time is being fired going toward the medulla to the cardiac center in the medulla. As soon as blood pressure increase, so over here, right? So when the pressure inside the blood vessel increase, it will expand, it will distend the wall of the blood vessel, either at the aortic arch or the coronary sinuses. And once that happens, that mechanical action, the expansion, activates these neurons, causing them, inducing them to increase the frequency of their action potential being produced per unit time. So here you see there's much more action potential being generated and transmitted back to the medulla oblongata, right? So that's how the central nervous system is being notified that the blood pressure in these blood vessels has been increased. And they're going to send it back, and then basically to bring everything back in homeostasis. Same thing here. When blood pressure drops, they send the frequency drops. So that's how the central nervous system knows about the pressure status in our blood vessels, right? So this is how blood pressure is maintained by the nervous system. So moving on to the next one. So we didn't actually leave the previous slide is related to this. So information coming from the heart, from these baroreceptor, is going through these this cardiovascular center, like I said, in the brainstem, more specifically our medulla. So this is the integration center. This is where the control center is. It's basically monitoring cardiovascular function 24/7, under, subconsciously. So you're not aware of this. We take all of this for granted. And once it receives it, it will shoot out, it will send out motor command. In this case here, it's visceral motor commands, right? Visceral autonomic motor decisions, meaning these motor activities, you are not consciously aware because they did not come from your cerebral cortex. So the cerebral cortex, again, is the seat of consciousness. So if nothing comes up to it and nothing comes down from it, then there's no consciousness involved, right? So this is the amazing part. This is tying together several lecture together. Let's begin with the sympathetic division first, okay? So the parasympathetic division, this is the rest and digest division of our visceral or autonomic nervous system, motor system. So this is activated, mobilized, let's say when you are relaxed, in a relaxed state, like after a meal, right? You want to relax, want to smoke a cigar, you know, having a cognac. There you go. That's when your parasympathetic division is completely on, right? Relax and digest. And this division sends post-ganglionic fibers to make contact, to make neuromuscular junction with the SA node of the heart. This is the conduction of the heart, meaning the electrical component of the heart. Electrical component, okay? So the parasympathetic division, in other words, can only affect the electrical component of the heart. It can only slow down the heart rate. So when we look at the equation CO equals HR times SV, there you go. The parasympathetic can only affect this part of the equation. Okay? The parasympathetic cannot, I repeat, cannot affect the mechanical component of the heart. It has no say in terms of the strength of contraction of the myocardium, the strength of contraction of a cardiomyocyte. Here comes the question. Why? Right? Again, that helps you to understand the material, not blindly memorizing everything. So the question is, why is it that the sympathetic division cannot affect the mechanical component of the heart? The answer is really straightforward. It's right in front of you on the slide itself. Right? If you look closely, this is the parasympathetic. You see that blue line there? It goes to the yellow dot, the SA node. Do you see that line going down here in the myocardium anywhere? No. So because the parasympathetic division does not make contact, does not have neuromuscular junction with the myocardium, right? With the cardiomyocyte, with the actual cardiac muscle cell that contract. Therefore, if it does not make contact with them, it cannot control them. Simple as that, right? So the parasympathetic division can only affect the rate of the heart, okay? So let's get that out of the way, the contribution of the parasympathetic division. Now moving on to the more important one, the sympathetic division. The fight or flight division of the autonomic nervous system. This division readies your body to face an emergency situations, right? Like I've mentioned that, you know, repeatedly, multiple times now. And that sympathetic affects both the electrical component of the heart, electrical component, and the mechanical component of the heart. So electrical component here, we express that as HR. And the mechanical component here, we express that as SV, stroke volume, okay? The sympathetic division can affect HR because it also targets the SA node. So if you look closely here, that green line goes to the yellow dot, the SA node. Okay, so the sympathetic division can increase the heart rate. The parasympathetic decreases the heart rate, drops the heart rate, but the sympathetic hikes up the heart rate, right? Makes the heart rate go higher, induces the heart to beat faster. So the sympathetic will induce the heart to beat faster. The parasympathetic will cause the heart, will slow down the heart rate, will cause the heart to beat slower. So let's erase them. So that's the sympathetic contribution to the electrical component of the heart. Now it also affects the mechanical component of the heart because it sends down axons making contact, forming neuromuscular junction with the myocardium. So it's basically this line over here, goes out over here, okay? Affecting the contractile cardiac muscle. So sympathetic will induce your cardiac muscle cell, your cardiomyocyte, to increase the contraction, increase tension. They will cause your heart to beat stronger, to squeeze stronger. So if you squeeze stronger, contract stronger, you will eject an amount of blood that will also be increased. In other words, if you increase the strength of contraction, SV, stroke volume, will also be increased. So that's how the sympathetic division affects the mechanical component of the heart. Okay? So we're done with the heart. Now, what about the blood vessels? So the sympathetic division here can also affect our vascular beds. 3 and 4 are vascular beds. So 3 is arterial and 4 is veins. So these are blood vessels. Okay? So the sympathetic division can constrict the blood vessels. Depending on the vascular bed, depending on the location of the vascular bed, perfusing the type of tissue, it can either constrict the blood vessel or it can dilate the blood vessel. We're going to come back to this very important concept when, for example, norepinephrine is causing constriction of blood vessels, whereas epinephrine can cause dilation of blood vessels. We're going to talk about that very important concept. But the point is, so the sympathetic here can affect the heart and the blood vessels, right? Cardiovascular. Sympathetic affects both. The heart, 2 components. It can affect the electrical component of the heart, mechanical component of the heart. So that's the heart. But it also have a say in the blood vessels, not only arteries, but also veins, specifically arterioles and veins. Okay. So that's the involvement, the contribution from the nervous system as an external control mechanism affecting the force driving blood forward. So moving on to the details here. Oh, I forgot to erase this. So the baroreceptor, it's so parasympathetic division. SD stands for sympathetic division, and so over here. And then PD stands for parasympathetic division. So what's going to happen? We talk about this. So arterial baroreceptor, it's detecting arterial pressure drops. Arterial receptor increases SD and decreases PD, meaning these receptors activates, mobilizes the sympathetic division and then put to sleep the parasympathetic division. Every time that they are being activated, every time that they detect a pressure change in our blood vessels, specifically in the aortic arch and in the carotid sinuses. I was about to say corona. I'm obsessed by that the current health crisis, guys. So sorry about that. Okay, so let's go over this stepwise, and bear with me here. Let's focus first on the root cause. Okay, so there's a drop in blood pressure, right? So MAP has been decreased. We take this for granted. It doesn't have to be any condition. It's like in the morning when you lie down and you stand on your foot right off the bat out of your bed, right? When you're young, your system picks up within seconds, less than a fraction of a second, everything comes back to normal. But when you get older, like the elderly, they cannot afford that. If they do that, they will fall, because their organ system, their system is not fast enough to rectify this sudden drop in blood pressure. And they can pass out, or they can basically lose consciousness, so on and so forth. But this is what happens. So when your MAP, M-A-P, mean arterial pressure, the driving force pushing blood through your vascular bed has been dropped, that decrease in pressure will be picked up by these baroreceptors, and it kickstarts a reflex. So this is what happens. The parasympathetic activity, it will decrease. So the SA note here, when you are basically dropping, preventing the parasympathetic activity, in other words, your heart cannot be slowed down, meaning it cannot be slowed and it's already at. Simultaneously, your sympathetic activity has been mobilized, activated. So both of them, parasympathetic and sympathetic, at the SA node here. Sympathetic in this case will win over and will cause the heart to beat faster. So HR will increase. So if you increase HR, what's going to happen? MAP will increase. Okay. So let's erase this part out of the way. Moving on to here, sympathetic activity again is activated. It's going to induce the cardiomyocyte to contract more forcefully. So the strength of contraction, the contractility of the myocardium has been increased. So when that happens, your stroke volume will increase. So the amount of blood coming out of the heart increase. Think about a balloon, right? The stronger you squeeze the balloon, and that balloon contains water inside, the stronger you squeeze the balloon outside in, the larger the amount of water will basically leave in that balloon. Same thing with the heart. So the stronger the heart squeezes, contracts, the larger the amount of blood will leave the heart. We call that the stroke volume. So if your stroke volume increases, then MAP also increase. So HR increase, SV increase will lead to MAP increase. Same thing here. So sympathetic affecting the heart, we just go over that. Let's take that out of the equation. But sympathetic, we mentioned earlier, it not only affects the heart, it also affects the blood vessels. In this case, let's focus on the veins. So if it increase the venomotor tone here, meaning the walls of the vein, the large vein can constrict somehow, decreasing the compliance, meaning increasing pressure. So increasing the venous pressure here, meaning increasing the venous return, meaning the amount of blood that goes back to the heart. So if you increase the amount of blood going back to the heart, then you increase the EDV and diastolic volume, right? That equation you have to rewrite here. Stroke volume equals EDV. This is from chapter 13, minus ESV and systolic volume, right? So this here depends on venous return, VR, the amount of blood that goes back to the heart. So if that venous return is increased, EDV is increased. If EDV is increased, SV will be increased, as you can see here. If SV increases, you go back here, MAP increases. Right? So that's the contribution from the sympathetic division on veins. Okay, I'm gonna take that out. And we also learned that the sympathetic also can affect arterioles by causing constriction of the arterioles. If you increase the constriction, you will increase TPR, resistance to flow. If you increase TPR here, you will increase MAP. So that's in response to a decrease in MAP by re-increases, right? So that's controlled by a negative feedback. So during all of this, the sympathetic is mobilized, activated, the parasympathetic has been put to sleep, right? It will be inhibited. So your sympathetic activity is completely on, okay? This is just due to a drop in the driving force, pushing blood forward. So your tissue perfusion will be compromised if this is not rectified, okay? So all this mechanism on this slide is to rectify this situation. If there's a decrease in the driving force pushing blood forward, that driving force must be reestablished. And that reestablishment is done by the sympathetic division of the autonomic nervous system, the fight or flight division of our visceral motor division of the nervous system. Okay. Such a beautiful story. I wish I could lecture this in a face-to-face setting. The past two lecture outline, chapter 3, chapter 12, chapter 13, chapter 14, they rival the nervous system unit in terms of complexity, in terms of beauty. So gorgeous. And then now I have to stare at the computer screen to share this with you. It's sickening. Okay. Moving on to the next one. So this is the involvement in the endocrine system affecting MAP. So we're going to focus on epinephrine. Yeah. Because vasopressin and angiotensin 2 here, that's I mentioned that briefly earlier, that angiotensin 2, this is one of the most, if not the most powerful, okay? I repeat, one of the most, if not the most powerful factor that causes vasoconstriction. It will constrict, it will cause your blood vessel to constrict, making their diameter smaller. ADH stands for antidiuretic hormone, also known as vasopressin, because they cause vasoconstriction in blood vessels. So they increase the pressure in the blood vessels, hence the name vasopressin. But I'm going to focus on epinephrine. Now it says here, epinephrine activate target tissues with binding to beta-1. That's not really accurate. Okay, I did that on purpose because this is straight from your book. Epinephrine in this case is released by the adrenal medulla. So we have the right adrenal medulla and the left adrenal medulla because we have two adrenal glands. So epinephrine is produced and released by chromaffin cells, okay? And this epinephrine is released into the bloodstream, and it will go and it will affect a lot of systemic tissues. So let me start with one step at a time. Epinephrine can affect beta-1 receptor as shown here. And when epinephrine affects beta-1, we are talking about cardiac tissue. There's a reason why I use the word tissue. When I say cardiac tissue, I'm talking about the electrical component of the heart, and I'm talking about the mechanical component of the heart. So what it means is epinephrine, by activating beta-1 through the electrical component of the heart, it will increase the heart rate. And through the mechanical component, it will increase the stroke volume because it increases the strength of contraction. It induces the cardiomyocyte to contract stronger. So pumping out more blood per heartbeat. Okay, so that's what you see here. Heart raises HR and SV. This, number one, that is due to epinephrine binding to beta-1 adrenergic receptors. Okay. Okay, so that's for epinephrine and beta-1. Let's erase this. Keep epinephrine. Epinephrine also can activate beta-2. And these beta-2 receptors, they are located in a smooth muscle on the walls of blood vessels that are perfusing, and I repeat, perfusing skeletal muscle and cardiac muscle. Okay. Again, these beta 2 receptors are on the cell or plasma membrane of smooth muscle cells that are lining, that are within the wall of blood vessels. And these blood vessels are perfusing skeletal muscles and cardiac muscles. So when epinephrine is released and they activate the beta 2 receptors, these blood vessels dilate. In other words, they allow blood to increase. More blood going to skeletal muscles, more blood goes to cardiac muscles. It makes sense because you need, under these cases, you're under emergency situations, your skeletal muscle must be ready for action, right? Fight or flight, right? Either you fight or you run away, right? So you need energy. If you need energy, you need more ATP. You need more ATP, you need more oxygen, and you need more glucose being delivered to you. You know, the only way to do that is increase blood flow. And to increase blood flow, you need the blood vessel to dilate. That's exactly what happens. Epinephrine activate beta 2, and then the blood vessels dilate. Only the blood vessels that are perfusing skeletal muscle and cardiac muscle. Okay. And obviously also, you know, the brain, you need blood perfusion to the brain as well. So that's beta 1 and beta 2. Now, epinephrine also can activate alpha 1. But there's a catch. Epinephrine will activate alpha 1 only if the concentration of epinephrine under high concentration. Because alpha 1 receptors do not have high affinity for epinephrine. So in order for epinephrine to have an effect on these alpha 1 receptors, you have to have high concentration of epinephrine. If you have low concentration of epinephrine, they don't respond. And this is important because the alpha 1 adrenergic receptor, they are also on the smooth muscle. And I need to have something to write better than this. Sorry, guys. Okay. So these alpha 1 receptors are located at the cell membrane or plasma membrane of smooth muscle cells that are in the wall of blood vessels that are perfusing systemic tissues. Most of the systemic tissues, most of the vascular bed, except down here, cardiac muscle and skeletal muscle, okay? So when you have high epinephrine running around and they start to activate alpha 1, the response is vasoconstriction, number 2 here. That's why I said most vascular bed. Most vascular bed excluding, not including skeletal muscle and cardiac muscle. Epinephrine will cause vasoconstriction under high concentration. Now, which leads me, I'm going to leave alpha 1 here. I'm going to erase, I'm not going to erase, I'm going to erase this. I'm going to erase this. I'm going to add something here, Ne. Norepinephrine. When norepinephrine is released, this is from a nervous system, right? So the nervous system, when norepinephrine is released, it activates alpha 1. So it causes vasoconstriction of blood vessels, okay? So what is important, when you have vasoconstriction, it means T will increase. So when you constrict the blood vessels, you increase TPR. And when you increase TPR, if you allow me to go back here, okay, if you increase TPR, you increase MAP, right? So that's when the nervous system comes in. The nervous system releases norepinephrine, affecting alpha-1 in your systemic vascular beds, excluding cardiac muscle and skeletal muscle. When you constrict these blood vessels, you increase the driving force pushing blood forward by the intervention of the nervous system. So moving back here. Okay, so let me repeat to summarize here. I know it's a lot of information, but if I can do it, so can you, okay? Okay, here it goes. So when the sympathetic division is activated, right, we can have norepinephrine released by the postganglionic neurons, or we can have epinephrine released by the adrenal medulla. Okay? If the postganglionic neuron releases norepinephrine, NE, the norepinephrine will activate alpha-1 adrenergic receptors. These are G protein coupled receptors. They will cause blood vessels to constrict. We call it vasoconstriction. If you do that, TPR will increase. Total peripheral resistance will increase. That's basically this equation here. Okay? So TPR. So when you constrict your blood vessels, systemic blood vessels, you increase TPR. So if you increase TPR, you increase the driving force pushing blood forward, MAP. That's norepinephrine. We also saw, and we talk about this, under sympathetic activity, the adrenal medulla releases epinephrine, acting as a hormone. So moving back here. So as epinephrine released by the adrenal medulla, it can activate 2 adrenergic receptors. Actually 3, right? It can activate beta-1, and the beta-1 are actually on the cell or plasma membrane of either pacemaker cells or the cardiomyocytes, right? So the beta-1 are exactly exclusively on cardiac tissue. We're not talking about smooth muscle here. So beta-1 receptors are located physically in the cell membrane of a pacemaker cells, autorhythmic cells, or in a cell membrane, plasma membrane of an actual contractile cardiomyocyte, cardiac muscle cell. So if epinephrine comes in and activate these beta-1 receptors, if it's binding to the beta-1 receptors on the pacemaker cells, it will make the heart beat faster. Okay, so going back here, the same equation, if you make the heart beat faster, you will increase MAP. Okay. Now, the same epinephrine acting on beta-1 receptors now on the cell membrane of a contractile cardiomyocyte, the actual cardiac muscle that contract, then it will induce the heart to contract stronger. oops, so this is the heart rate, sorry. So this is the pacemaker, and this is the stroke volume, okay? So I take that back. So beta 1 on the pacemaker cell is increasing HR, MAP increases. Beta 1 on the cardiac contractile cell is SV. So stroke volume increase, MAP also increases, right? So epinephrine acting on beta 1, affecting both components of the heart, affecting the electrical component of the heart, affecting the mechanical component of the heart. Epinephrine acting on beta 2 receptors. These beta 2 receptors are on the cell membrane, plasma membrane of smooth muscle cells in the walls of blood vessels that are perfusing skeletal muscles and cardiac muscles. In those two cases, epinephrine causes these blood vessels to dilate, vasodilation, allowing more blood to come in, increasing blood perfusion locally. So both muscles, cardiac muscle and skeletal muscle, can receive more oxygen, can receive more nutrients, and also can dispose more carbon dioxide, more waste, because they have increased metabolic activity under emergency situations. The same epinephrine, if it's high concentration, it will also able to bind and activate alpha-1 adrenergic receptor. And these are the same ones that are activated by norepinephrine. They are located on the cell membrane of smooth muscle that are in the wall of blood vessels, perfusing systemic vascular beds, excluding skeletal muscle and cardiac muscle. And in this case, epinephrine acting on alpha-1 will cause vasoconstriction, increasing TPR. So TPR here will also increase, increasing MAP. And on that note, I will end the lecture. I hope you enjoy it. Let me see if I can do this. And then until the next time, so you guys take care, stay safe, stay healthy, be happy, and I'll talk to you soon, okay?